July 1st, 2025. Astronomers detect a massive comet tearing through our solar system at staggering 130,000 miles per hour. Initially, 3I/Atlas appears to be just another cosmic wanderer, but its trajectory tells a different story. A hyperbolic orbit with an eccentricity approaching 6, definitively confirming its interstellar origins. Then comes a real bombshell. At 6 times the Earth-Sun distance, far beyond where water ice could possibly sublimate, this mysterious object violently erupts with powerful jets. The James Webb Space Telescope reveals something unprecedented. Its coma consists of 99% carbon dioxide, with almost no water whatsoever. The fundamental rules of comet chemistry have been turned completely upside down. Is this the opening chapter of a cosmic mystery that science is now racing desperately to unravel? When the Atlas Survey Telescope in Chile first flagged this new object on July 1st, 2025, the initial data triggered a cascade of urgent calculations. This was clearly not just another icy wander drifting in from the distant Oort cloud. Its orbital eccentricity, nearly 6, immediately stood out as extraordinary. Most comets trace elongated elliptical loops, gravitationally bound to the sun. Not this one. With an eccentricity so dramatically above 1, its path is distinctly hyperbolic, meaning it will never return. This is a visitor from beyond our solar neighborhood, making a single swift pass through our planetary system before disappearing back into the vast emptiness of interstellar space. The object quickly received its formal astronomical designation, 3I/Atlas. The I designates it as only the third confirmed interstellar object ever detected, following the enigmatic Oumuamua and the mysterious 2I/Borisov. But there's a crucial difference that sets 3I/Atlas apart. Early photometric observations suggested a nucleus measuring up to 15 kilometers across, making this interstellar visitor not just an outlier in terms of trajectory, but in sheer physical size as well. That's hundreds of times the surface area of Borisov and orders of magnitude larger than Oumuamua, which was closer in scale to a city block than a small country. Even the lower bound estimates, based on Hubble Space Telescope observations and calculations of the object's reflectivity, place it firmly in the multi-kilometer class. This scale mattered profoundly. A nucleus this large carries substantially more thermal inertia, meaning it should respond more slowly to solar radiation and be far less prone to sudden, dramatic outbursts. Yet, paradoxically, its brightness and the enormous size of its coma don't conform to the standard comet template at all. Surface area calculations, accounting for the observed magnitude and assumed albedo, suggest a body with enough real estate to host entire towns, all wrapped in a cloud of gas and dust stretching tens of thousands of kilometers across space. Compared to its interstellar predecessors, 3I/Atlas exists in a league entirely of its own. Oumuamua was a tumbling, elongated sliver of unknown composition. Borisov appeared more like a conventional comet, but remained modest in scale. This new arrival is a heavyweight champion, barreling through our solar system on a path that will never curve back. Its mass and momentum serve as stark reminders that most interstellar objects passing through our neighborhood are either too small or too faint to ever be detected. For something this massive to appear and to be moving this fast is statistically extraordinary, perhaps even unprecedented. That's precisely why astronomers worldwide are monitoring it with such intense scrutiny. When a country-sized chunk of ancient ice and rock from another star system flies through our cosmic backyard, every observable detail becomes a precious clue to understanding what's possible beyond our sun's domain. Out beyond Jupiter's orbit, where sunlight diminishes to little more than a distant, feeble glow, 3I/Atlas began to stir. Astronomers tracking its trajectory expected complete silence. At 6.4 astronomical units from the sun, ambient temperatures hover far below what's required to awaken a typical comet. Water ice, the usual culprit behind cometary activity, remains frozen solid until approximately 3 astronomical units from the sun. Yet telescopes recorded something astonishing, a bright, rapidly expanding shroud of gas and dust enveloping the nucleus, an unmistakable signature of vigorous outgassing. The sheer scale of this activity caught the scientific community completely off guard. Calculations based on the coma's brightness and the estimated size of the nucleus, up to 15 kilometers across, revealed that more than 20% of the surface was already actively venting material into space. That represents a level of activity rarely witnessed, even among the most hyperactive comets in our solar system, and it's virtually unheard of at such a vast distance from the Sun. For comparison, most comets manage only a few percent of their surface actively jetting material, and only when they venture much closer to solar heating. This early and intense outpouring defied every standard model of comet physics. The solar energy available at 6.4 astronomical units is simply far too weak to account for such robust outgassing if water ice were the primary driver. The numbers refuse to add up. Something else, some other volatile substance, or perhaps a unique structural characteristic, had to be fueling these premature, powerful jets. Monitoring teams began meticulously scrutinizing every available data point, searching desperately for clues in the evolving coma as the object continued to shatter every established rule in the comet playbook. The normal boundaries of the so-called water-ice sublimation line seemed utterly meaningless here, leaving astronomers grappling with profound puzzle that pointed well beyond familiar thermodynamics. The James Webb Space Telescope turned its powerful infrared gaze toward 3I/Atlas just as the comet's anomalous activity was raising serious questions throughout the astronomical community. Spectroscopic observations from JWST's NIR-SPEC instrument delivered results that fundamentally upended every expectation. The coma is composed almost entirely of carbon dioxide, a discovery that contradicts everything we know about cometary composition. The numbers are absolutely stark and undeniable. Carbon dioxide outgassing was measured at 129 kilograms per second, while water vapor barely registered at a mere 6.6 kilograms per second. That establishes a carbon dioxide to water ratio of roughly 20-1, a value that stands 6 standard deviations above the trend observed for any long period or Jupiter family comet in our solar system. In percentage terms, nearly 95% of the detected gas is carbon dioxide, with water comprising less than 5% of the total composition. Even among the handful of solar system comets known for relatively high carbon dioxide content, none even remotely approach this extreme profile. JWST's detailed spectra also revealed a coma remarkably rich in tholins, complex organic molecules that give the dust cloud a distinctive deep reddish hue. Tholins form when organic ices are exposed to intense ultraviolet radiation over millions of years, strongly suggesting a surface that has been weathered and processed during prolonged interstellar travel. This signature appears as a broad absorption feature in the near-infrared spectrum, representing a fingerprint of extensive UV processing rarely observed in solar system comets. The scientific team behind the JWST Observing Campaign, led by Dr. Michael S.B. Kelly and his collaborators, confirmed these extraordinary findings through repeated observations. Each observation pass yielded identical results, the same inverted chemistry. Carbon dioxide overwhelmingly dominates. Water remains a trace component. Carbon monoxide and carbonyl sulfide appear in small amounts, but nothing approaches the runaway carbon dioxide production rates. The spectral lines are unambiguous and reproducible. This is categorically not a comet that fits any standard model. Instead, 3I/Atlas displays a molecular fingerprint that has never been cataloged before in cometary science, and it's forcing researchers to fundamentally rethink what's chemically possible when a visitor arrives from far outside our sun's gravitational and chemical domain. Carbon dioxide dominates the story of 3I/Atlas not merely in terms of chemistry, but in the underlying physics that drives its bizarre behavior. Most comets remain dormant until they venture close to the sun, inside about 3 astronomical units, before solar radiation can rouse their water ice into sublimation and activity. But 3I/Atlas began violently venting gas far beyond that threshold, out past Jupiter's orbit where temperatures are theoretically too low for water ice to sublimate at any significant rate. The answer to this mystery lies in the highly volatile nature of carbon dioxide ice. Unlike water ice, carbon dioxide can transition directly from solid to gas at temperatures as low as 20 to 30 Kelvin, which means even the faint warmth of distant sunlight at 6 astronomical units provides sufficient energy to trigger sublimation. The nucleus, estimated at up to 15 kilometers in diameter, is almost certainly not a solid, monolithic block of ice. Instead, computational models strongly suggest a highly porous internal structure riddled with carbon dioxide-rich pockets and voids, something resembling cosmic Swiss cheese at a massive scale. As weak sunlight gradually penetrates the surface, carbon dioxide trapped deep within these internal voids begins to sublimate. Gas pressure builds inexorably in confined spaces beneath the surface layers, eventually forcing its way violently outward through narrow vents or structural weak points. These jets can erupt with surprising force, carrying not only gas but also dust particles and even large ice grains with them, fully explaining the early, robust coma detected in telescope observations. The internal pressure within these subsurface pockets depends critically on the size distribution of the pores and the thermal conductivity of the surrounding material. In some regions, even a modest temperature increase can trigger a sudden, catastrophic release, sending jets of carbon dioxide gas streaming into space at velocities reaching hundreds of meters per second. Thermal models developed from studying comets like 67P/Churyumov-Gerasimenko have demonstrated that even a modest gradient in porosity can efficiently funnel sublimating gas toward the surface, concentrating activity into localized patches or jets. For 3I/Atlas, observational evidence suggests that more than 20% of the total surface area appears to be actively venting gas, an unusually high fraction for a comet of this substantial scale. The energy required to sustain this level of activity is supplied by solar radiation, but the remarkable efficiency comes from the internal structure itself. High porosity, low thermal inertia, and a favorable distribution of carbon dioxide ice concentrated near or at the surface. The result is a celestial body that can erupt with dramatic activity long before water-ice sublimation becomes relevant, defying conventional wisdom about cometary behavior. The extraordinary chemistry observed in 3I/Atlas points compellingly toward an origin far outside the familiar chemical environment of our solar system. Thick disk stars, older stellar populations that are significantly depleted in heavy elements, shape their protoplanetary disks according to very different rules. In these metal-poor, oxygen-starved environments, the carbon dioxide snow line extends much farther from a parent star, and the delicate balance of available ices shifts dramatically compared to our own solar nebula. Instead of producing water-rich bodies like those that form throughout our solar system, a comet born in a thick disk environment around such a star could be predominantly loaded with carbon dioxide and other hypervolatile compounds. The remarkably high carbon dioxide to water ratio observed in 3I/Atlas's coma, paired with tantalizing hints of isotopic differences from solar system norms, strongly supports the hypothesis that this object condensed from a protoplanetary disk operating under a fundamentally different chemical recipe, one that left it primed from birth to violate every established rule in the conventional comet playbook. Avi Loeb, the Harvard astrophysicist renowned for championing unconventional and bold possibilities in astronomy, has publicly called 3I/Atlas the most promising test case yet for what he terms the alien artifact hypothesis. He draws particular attention to the comet's nearly retrograde orbit, 175 degrees inclination, which slices through our solar system on a trajectory lying only 5 degrees off the ecliptic plane. That specific geometric configuration is rare enough to raise serious questions among orbital dynamicists who study celestial mechanics. But Loeb's primary focus extends beyond mere orbital mechanics to encompass the timing and the chemistry. He emphasizes that 3I/Atlas will reach perihelion, its closest approach to the Sun, on October 29, 2025, precisely as it swings behind the Sun from Earth's observational perspective. For Loeb, this geometric arrangement feels almost too convenient, as if the object were deliberately designed to pass directly through the planetary plane, making close approaches to Mars and even skimming relatively near Jupiter before vanishing back into the interstellar darkness from which it emerged. The argument isn't confined to orbital peculiarities. Loeb and his colleagues highlight the comet's photometric variations. The conspicuous absence of any classic water ice surged despite approaching the Sun, and most provocatively, the completely inverted chemistry that defies all precedent. They pose a challenging question. If this visitor is entirely natural, why doesn't it behave like any other comet humanity has ever studied? Why does its coma remain almost pure carbon dioxide with water, vapor barely detectable even as solar heating intensifies? In low provocative view, such a profound anomaly demands that we seriously consider extraordinary explanations. Could 3I/Atlas possibly be a disguised probe of artificial origin? Could its carbon dioxide jets represent a clever disguise or propulsion system for something fundamentally artificial? Or is it perhaps a completely natural body originating from a star system where planetary chemistry operates in reverse from our expectations, a place where carbon dioxide, not water, dominates planetary formation? As 3I/Atlas continues its swift journey toward perihelion, every major telescope on Earth and in orbit will be watching intently for potential water surge. If the comet's water production suddenly and dramatically spikes as it approaches maximum solar heating, then standard cometary models will be vindicated and the mystery will largely dissipate. But if water production remains stubbornly low, if the coma continues to be dominated by carbon dioxide even at peak solar radiation, then the anomaly will stand unchallenged, and the case for something truly novel, or perhaps something truly strange, will grow substantially stronger. The scientific countdown to October 29th, 2025, has begun in earnest. Until that critical day arrives, 3I/Atlas stands as direct, undeniable evidence that our solar system represents just one possible outcome of planetary formation, and that cosmic chemical diversity is far greater than scientists once believed possible. Whether this mysterious visitor proves to be an exotic natural body from an alien star system or something even more extraordinary remains an open question, one that will be answered in the coming months as this cosmic enigma makes its closest approach to our sun before departing forever into the infinite darkness of interstellar space. October 28th, 2025, 2347 Universal Time Coordinated. Less than 24 hours before perihelion, and the astronomical community is operating on minimal sleep and maximum caffeine. Observatories across 3 continents have coordinated an unprecedented observation campaign. The Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope, and dozens of smaller facilities are all trained on a single point in space where 3I/Atlas is about to make its closest approach to the Sun, a mere 0.65 astronomical units, while inside the orbit of Venus. Dr. Sarah Chun, lead coordinator for the Global Observation Network, hasn't left the operations center at NASA's Jet Propulsion Laboratory in 3 days. Her team's monitors display real-time data feeds from around the world, each screen showing a different wavelength, a different perspective on the cosmic visitor that has consumed their lives for the past 4 months. The atmosphere in the room is electric with anticipation and dread. They're about to witness something that will either confirm or shatter everything they think they know about comets. JWST data coming through now, announces Dr. Marcus Rodriguez from his station. Spectroscopic analysis processing. The room falls silent except for the soft hum of computers and the distant whir of air conditioning. Every eye fixes on the central display as colored lines begin tracing across the spectrum analyzer. The familiar carbon dioxide signature blazes bright and strong. But there, right there in the wavelengths where water should be screaming its presence at this proximity to the sun, there's almost nothing. Water production rate holding at 7.2 kilograms per second. Rodriguez continues, his voice carefully neutral but edged with something that might be awe or fear. Carbon dioxide at 342 kilograms per second and climbing. The ratio is getting worse, not better. Dr. Chen feels her heart hammering against her ribs. This isn't supposed to happen. At 65 cents, with solar radiation intense enough to make surface temperatures soar, water ice should be sublimating furiously. Every model, every simulation, every piece of conventional wisdom about cometary behavior demands it. Yet 3I/Atlas continues to defy reality itself. We're getting something else, interrupts Dr. Yuki Tanaka from the photometry station. Activity spike on the sunward side. I've never seen outgassing rates like this. The jets are intensifying, but it's still almost pure CO2. How is this possible? October 29th, 2025, 1423 Universal Time Coordinated. Perihelion. 3I/Atlas reaches its closest point to the sun, and something extraordinary happens. The VLT's high-resolution imaging captures at first a sudden, dramatic change in the coma's structure. Instead of chaotic, diffuse cloud typical of comets at perihelion, 3I/Atlas's coma reorganizes into what appears to be a series of discrete, symmetrical jets. For primary streams, evenly spaced around the nucleus, pulsing with mechanical regularity. Are we seeing this correctly? Dr. Chin demands, leaning over Tanaka's shoulder to scrutinize the images. Those jets, they're too regular, too symmetrical. The pattern is undeniable. While natural comets can certainly produce multiple jets from different active regions, they typically vary in intensity and direction based on the irregular topography of a nucleus and the uneven distribution of volatile ices. These jets look almost engineered. They pulse in a rhythm, 3 seconds of intense outgassing, followed by 2 seconds of reduced activity, then repeating, over and over. Could it be rotation? Suggests Dr. Michael Patel, the team's dynamicist. If the nucleus is spinning and has exactly 4 major vents at the cardinal points, the rotation period doesn't match, Tanaka interrupts, pulling up the photometric data collected over the past months. We established a tumbling rotation with a period of 8.7 hours. This pulsing pattern operates on a 5-second cycle. They're completely independent. The room erupts in a dozen simultaneous conversations, voices rising as scientists grapple with the implications. Dr. Chin raises her hand for silence, but her mind is racing through possibilities, each more unsettling than the last. Avi Loeb's voice crackles over the conference line from Harvard. He's been listening to the data stream in real time. The pattern you're describing. Has anyone considered that you might be observing control venting? Not geological, but technological. The suggestion hangs in the air like a physical presence. No one speaks for several long seconds. Avi, that's... Dr. Chin begins, then stops. What can she say? That is impossible? They've been watching the impossible unfold for 4 months. That is statistically improbable? So is everything else about 3I/Atlas. We need more data. October 29th, 2025, 1915 Universal Time Coordinated. 5 hours past perihelion, and 3I/Atlas is beginning its outbound journey. The object is now positioned behind the sun from Earth's perspective, making direct observation temporarily impossible. But radio telescopes aren't limited by optical line of sight. The Very Large Array in New Mexico, operating at its maximum sensitivity, has been monitoring 3I/Atlas across multiple radio frequencies throughout its perihelion passage. Dr. James Wu, the facility's director, is reviewing the data when something catches his attention, a narrowband signal at 1.42 gigahertz, the hydrogen line, one of the most significant frequencies in radio astronomy. At first, he assumes it's interference, perhaps from a satellite or terrestrial source. But the signal is clearly coming from the direction of 3I/Atlas. Moreover, it's not continuous. It pulses, on for 3 seconds, off for 2 seconds, then repeating. The same pattern as the visual jets. Wu's hand shakes slightly as he runs the signal through multiple filters, checking and rechecking the source coordinates. There's no mistake. The signal originates from 3I/Atlas, and it's far too coherent, too narrow-band, to be a natural process. Natural radio emissions from comets are broadband and chaotic, generated by the interaction of solar wind with the coma. This is something entirely different. He immediately contacts Dr. Chun at JPL. Sarah, we have a problem. Or discovery. I honestly don't know which. October 30th, 2025. The news breaks despite attempts to contain it. A radio astronomer at Arecibo, recently reopened after its reconstruction, independently detected the same signal and, unaware of the sensitivity of the data, published preliminary findings on a preprint server. Within hours, the story explodes across global media. Alien signal from interstellar comet? Is 3I/Atlas an extraterrestrial probe? Scientists detect artificial pattern from space visitor. The headlines range from cautiously skeptical to wildly sensational. Social media erupts with theories, fears, and excitement. Governments quietly convene emergency scientific advisory meetings. The United Nations hastily organizes a special session. Meanwhile, 3I/Atlas continues its journey, now moving away from the sun at 130,000 miles per hour, accelerating as it climbs out of the sun's gravity well. Dr. Chen finds herself thrust into the center of a global maelstrom. At JPL, her team has been joined by representatives from NASA headquarters, the Department of Defense, the NSA, and a dozen international space agencies. The pressure is immense. They need answers, and they need them now. But the truth is, they don't have definitive answers, just increasingly disturbing questions. The radio signal continues, unchanging in its regularity, as 3I/Atlas pulls away from the inner solar system. JWST manages one more spectroscopic observation before the object moves beyond optimal range, and the results only deepen the mystery. The carbon dioxide to water ratio remains inverted. The Tholen signature is stronger than ever, and buried in the near-infrared spectrum. Dr. Rodriguez discovers something that makes his blood run cold, absorption lines that match no known molecule in any database. It's possible they're complex organics we've never cataloged, he tells the assembled team, though his voice lacks conviction. Or it's possible we're looking at synthetic compounds, materials that don't form naturally. November 3rd, 2025. For days past perihelion, an orbital dynamicist noticed something that sends a new shock wave through the scientific community. 3I/Atlas is accelerating faster than it should be. Comets naturally experience non-gravitational acceleration due to the rocket effect of outgassing, jets of sublimating ice acting like tiny thrusters. This is well understood and predictable, but 3I/Atlas's acceleration doesn't match the observed outgassing rate. The object is moving faster than the carbon dioxide jets alone can account for. Dr. Patel runs the calculations 3 times, then asks 2 colleagues to independently verify. The result is always the same. 3I/Atlas is experiencing an excess acceleration of approximately 3.2 times 10 meters per second squared. It's a tiny value, but in the precision world of orbital mechanics, it's as obvious as a neon sign. It's not impossible. Patel explains to the crisis team. Oumuamua showed similar excess acceleration, which is why some people, he glances at Loeb's video feed, suggested it might be artificial. But there are natural explanations. Outgassing from the night side that we can't directly observe. Sublimating supervolatiles even more reactive than CO2. Thermal radiation pressure if the object has an unusual shape or albedo. But, prompts Dr. Chun. But combined with everything else, the chemistry, the radio signal, the geometric jets, it's another data point that doesn't fit the natural comet hypothesis as cleanly as we like. November 5th, 2025. Dr. Aisha Okafor, a SETI researcher at the Berkeley SETI Research Center who has been analyzing the radio signal for the past week, requests an emergency video conference with the JPL team. I think the signal might be more than just a pattern, she announces without preamble. I think it might be a message. She shares her screen, displaying a complex analysis of the signal's structure. It's not just a 3-on, 2-off pulse pattern. Within each pulse, there are micro variations in amplitude and phase. They're subtle, easy to miss if you're not looking for them, but they're there and they're not random. The visualization shows the signal broken down into its component parts, revealing layers of structure nested within structure. Binary patterns emerge, then more complex modulations that could represent higher-order information in coding. I need to be clear, Okafor continues. I'm not saying this is a message. I'm saying it has information-theoretic properties consistent with encoded data. The entropy measurements, the compression ratios, the non-random distribution of symbol frequencies, these are all signatures we'd expect to see in artificial communication, not natural phenomena. Can you decode it? Ask someone from the NSA contingent. We're trying, but without knowing the encoding scheme, the language structure, or even the basic unit of information. Okafor shakes her head. It's like trying to translate a completely unknown language with no Rosetta Stone. We can identify that it probably is language, but reading it, that could take years, decades, or might be impossible. November 12th, 2025. 3I/Atlas is now 1.8 astronomical units from the Sun and rapidly receding. The object remains active, though the coma is slowly fading as solar heating decreases. Telescopes are pushing their capabilities to their absolute limits to squeeze out every last observation before the visitor vanishes back into the cosmic dark. The radio signal continues, unchanged, like a cosmic heartbeat that refuses to stop or vary. The geometric jets have become less pronounced as activity levels drop, but when visible, they still maintain their eerie symmetry. The excess acceleration persists, precisely measurable despite the object's increasing distance. Dr. Chen stands alone in the JPL Observation Center at 3 a.m., staring at the wall of displays, showing 3I/Atlas's diminishing light. In 6 weeks, it will be too faint for even Hubble to track. In 6 months, it will pass beyond Neptune's orbit. In a few years, it will leave the solar system entirely, carrying its secrets with it. Her team has compiled a comprehensive report for NASA, the international scientific community, and various government agencies. The document carefully presents all the evidence, explores natural explanations for each anomaly, and acknowledges a possibility, however unsettling, that 3I/Atlas might not be entirely natural. The report's conclusion is necessarily cautious. Based on available evidence, we cannot definitively determine whether 3I/Atlas represents an exotic natural object from a chemically anomalous stellar system or an artificial probe of unknown origin. Further observations during the object's outbound journey are strongly recommended. But Chen knows what she believes, even if she can't prove it. She spent 4 months watching this object defy every expectation, break every rule, and exhibit patterns that border on impossible. The scientist in her demands more evidence, better data, irrefutable proof. The human in her already knows the answer. December 25th, 2025, Christmas morning. Most of the world is distracted by holidays and family, but a small network of observatories continues their vigil over 3I/Atlas. The object is now barely visible, a faint smudge against the background stars at magnitude 23.5, detectable only by the most powerful instruments. At 8:42 Universal Time Coordinated, the radio signal stops, not fading gradually as might be expected from increasing distance, but terminating abruptly mid-pulse. One moment it's there, the 5-second pattern continuing as it has for nearly 2 months. The next moment, silence. Dr. Wu at the VLA immediately checks all systems, fearing equipment failure, but the array is functioning perfectly. They're simply receiving nothing from 3I/Atlas's position. He contacts other radio facilities, Arecibo, the Allen Telescope Array, the Murchison Wide Field Array in Australia. All report the same thing. The signal has ceased. The news spreads quickly through the scientific community, despite the holiday. Theories proliferate. Perhaps the transmitter failed, or the object rotated to point the beam away from Earth, or maybe its mission, whatever that mission was, has concluded. Or perhaps, some speculate, the object simply finished saying whatever it needed to say. January 15th, 2026. 2.5 months after perihelion, 3I/Atlas crosses 3 astronomical units outbound, and the last dedicated observations are made. The object has fallen silent in all wavelengths. The excess acceleration has gradually decreased, though it never entirely matched predictions based on observed outgassing. The mystery compounds remain unidentified. Avi Loeb publishes a comprehensive paper arguing that the preponderance of evidence suggests artificial origin. The paper is immediately controversial, drawing both support from researchers who believe the anomalies are too numerous to ignore and fierce criticism from those who insist that exotic natural explanations, however improbable, remain more likely than extraterrestrial technology. The scientific debate rages on, but 3I/Atlas itself recedes beyond detection, beyond reach, beyond any hope of follow-up investigation. Humanity's first potential encounter with alien technology, if that's what it was, has come and gone. The visitor delivered its strange message or completed its enigmatic survey and departed, leaving behind more questions than answers. Dr. Chen stands in her backyard in Pasadena on a cold January evening, staring up at the stars. Somewhere out there beyond sight and knowledge, 3i/Atlas continues its journey into the infinite, accelerating toward what destination? Carrying what cargo of information back to what distant builders? She thinks about the report gathering dust on congressional shelves, about the decoded portions of the radio signal that reveal mathematical constants, but nothing comprehensible about the unknown molecules in the spectrum that might be complex organics or might be synthetic materials. She thinks about the timing, the geometric precision of its orbit, the symmetry of its jets, the sudden silence of its signal. Most of all, she thinks about what comes next. If 3i/Atlas was natural, it represents a revolution in our understanding of planetary formation and cometary chemistry. If it was artificial, it represents proof that humanity is not alone and that the universe is populated by intelligence capable of engineering objects that can survive interstellar journeys. Either way, nothing will ever be quite the same. The International Astronomical Union has already established a new protocol. Any future interstellar object will be subjected to immediate, comprehensive study with every available instrument. Funding has been allocated for a dedicated rapid response space mission that could potentially intercept and study, or even retrieve samples from the next visitor. Radio telescopes have been allocated additional time to monitor the sky for similar signals. Because everyone knows now that there will be a next time. The galaxy is vast, and objects drift between the stars. How many others are out there? How many have already passed through our solar system undetected? And how many more are on their way? 3i/Atlas may have departed, but left behind something more valuable than any decoded message. The certainty that we are living in a universe far stranger and more populated than we imagined. Somewhere out there, across the unfathomable distances of interstellar space, something, natural or artificial, mindless or intelligent, sent an object into our solar system, and we were here to witness it. Dr. Chin shivers in the January cold and goes back inside, but she knows she'll be back out tomorrow night, and the night after, and every clear night for the rest of her life, searching the darkness, waiting for the next visitor, because now they know what to look for. And the universe has proven that it has surprises to share.